Hello everyone, we are Hyperstella, and we are dedicated to developing Aurora, a female safety protection system based on FMCW radar technology. This system is designed to create a safer living environment for women. In recent years, women's safety has become an increasingly prominent issue. According to the World Health Organization, approximately 30% of women globally have experienced intimate partner violence, yet less than 40% of these incidents are reported. In China, millions of women annually face various forms of safety threats, from domestic violence to harassment in public spaces. These issues often go undetected and unaddressed in a timely manner. Many women find it difficult to seek help when in danger, especially within the home environment. Such incidents have sparked widespread societal concern about women's safety. Even more worrying is that many women, when threatened, are unable to call for help because they cannot access communication devices. The Aurora project was born out of this need, aiming to provide invisible protection for women through FMCW radar technology. Our system can discreetly detect abnormal situations in indoor environments, including sudden violent movements, dangerous verbal cues, and tense breathing patterns, thereby providing early warning and protection in the nascent stages of danger. Our project not only embodies technological innovation, but also carries deep social responsibility. By making invisible threats visible, Aurora echoes the feminist concept of making the invisible visible, offering technological support to vulnerable groups and promoting societal awareness and attention to women's safety issues. In the upcoming demonstration, we will elaborate on how the Aurora system safeguards women's safety and well-being by detecting 3 key signals: dangerous verbal cues, sudden movements, and changes in breathing patterns. Let's witness together how technology can empower women's safety and how every woman can achieve the security and happiness they deserve. First, we will demonstrate the hardware connection process of the radar system. We are using a TI-AWR 1843 FMCW radar, which operates at 60 to 64 GHz and can detect targets up to 8 meters away. We use DuPont wires to connect the USB to TTL adapter to the radar module. Carefully match the connections: 3.3V to 3.3V, GND to GND, and cross-connect TX and RX. Make sure the wire colors on both ends remain the same. Next, plug the USB into your computer. When the red indicator light turns on, open the SSCOM tool, set the port to COM3 and the baud rate to 921,600. Then send at plus reset and at plus start in sequence to begin radar data transmission. Now we will demonstrate the radar data collection interface. First, there's the parameter settings area, where we can configure the number of frames the radar will acquire this time, the acquisition angle, distance, acquisition scene, and the type of data to be collected. Finally, we assign an ID to this acquisition session. This is the real-time data acquisition log window. Once we click Start Acquisition, it will display the acquisition progress, such as which frame is currently being collected and whether the collection is complete. Finally, when all data has been acquired, it will show where the data was saved and how long the entire process took. Next, we introduce our custom GUI interfaces designed for classifying radar range speed maps, tailored for lip movements, body movements, and respiration and heartbeat signals. To ensure accuracy, we integrate MATLAB and Python, employing multiple models for training. 1. Lip Movement Behavioral Risk Classification Interface. This interface analyzes radar-acquired lip movement data to assess risk. Users load range speed maps with lip features. Clicking Predict displays simultaneous results from 5 models: Logistic Regression, SVM, Random Forest, KNN, CNN, intuitively marked Safe or Dangerous. 2. Body Movement Type Recognition and Training Interface. This GUI focuses on body movement, classification, and model training. Upload Image folder allows bulk upload of movement feature datasets for deep learning model training. Start training initiates the process, reporting accuracy and model-save path upon completion. It also supports single image prediction for instant classification of individual movement range speed maps. 3. Respiration and heartbeat vital signs analysis interface. The Life Signal Analysis System, GUI, is for respiration and heartbeat analysis. Users input the raw data file path and click Start Analysis. The system automatically processes and displays 3 graphs: phase signal decomposition, respiratory signal waveform, and heartbeat signal waveform, aiming to visually validate radar's effectiveness in extracting human vital signs. In radar data collection, we fully considered individual differences and gender differences. Using a small sample high-efficiency strategy, we recruited 13 participants, 8 females, 5 males, and achieved excellent results. The data includes 260 samples for mouth shape recognition, dangerous, safe binary classification, 520 samples for motion recognition, kick, punch, static, slap 4-class classification, and 29 respiratory cardiac data samples, validated against Huawei and Apple Watches. This small sample but high-quality strategy demonstrates the effectiveness of our approach. Now, we will demonstrate the data collection process of the lip reading module in the Aurora system. At this stage, the demonstrator needs to face the radar equipment directly, maintaining a distance of approximately 20 centimeters from it, and clearly pronounce the designated keywords to accurately capture the millimeter wave radar characteristic signals during the process of lip movement changes. This collection focuses mainly on the key mouth shapes that may occur in domestic violence scenarios. We have selected 2 representative English words, safe and dangerous. The collection process for each word involves a total of 5 frames of data. The first 2 frames are used for lip movement preparation and transition. After the second frame, the system begins to officially collect the key pronunciation features, ensuring that the data accurately covers the key stages of pronunciation. Through this module, Aurora can still recognize the user's plea mouth movements even when they are unable to speak or have limited language abilities, providing technical support for silent calls for help in dangerous situations. Next, we will present the data collection process of the motion recognition module in the Aurora system. To simulate potential dangerous behaviors, we selected 4 representative actions for collection and testing, covering typical upper limb and lower limb attack behaviors as well as the static state: slap, punch, still, kick. Each action's data collection process involves a total of 4 frames. It is uniformly stipulated that the formal collection begins after the first frame ends to ensure the capture of the key feature segments of the action. Data collection is repeatedly carried out by multiple test personnel from different angles and intensities to enhance the model's adaptability and generalization ability to different individuals and action variations. This module helps the system promptly identify dangerous behaviors and issue warnings, building real-time monitoring capabilities for violent behaviors. Finally, we will demonstrate the breathing recognition module in the Aurora system. Aurora can sense the subtle fluctuations in the chest cavity non-contactingly, thereby capturing the user's breathing status. During the test, the presenter collected data in 3 states: normal breathing, rapid breathing, and deep breathing. You can see the real-time waveform graph on the screen. Changes in breathing rhythm will directly be reflected in the differences in waveform frequency and amplitude. To verify the accuracy of the system, we simultaneously used Huawei and Apple smartwatches for reference measurement. The results showed that the recognition data of Aurora was highly consistent with that of the smart devices, demonstrating good reliability. This module can be used to identify abnormal physiological states such as tension and fear, and is an important component of the system's early warning mechanism. We process the collected MAP files into range Doppler maps as follows. First, A Fourier transform is performed on the raw ADC data collected from each antenna channel along the fast time dimension. This extracts the range information of the echo signal within each chirp, yielding the range profile. Subsequently, at each range bin, a Doppler FFT is executed along the slow time dimension. This is used to analyze the Doppler frequency shift at that specific range, thereby obtaining the target's radial velocity information. Finally, a two-dimensional range Doppler map is generated. We performed four-class classification on action images using a convolutional neural network, CNN. The dataset was split 8:2 into training and validation sets. Our CNN architecture included convolutional, pooling, fully connected, and classification layers. Training used the ReLU activation function and Atom optimizer for up to 10 epochs. The network extracted features via convolutional layers and optimized weights through backpropagation. Final results showed 95% training accuracy and 80% test accuracy, indicating good generalization. We performed binary classification on lip-shaped data to distinguish safe from dangerous words. We trained models using logistic regression, SVM, random forest, KNN, and CNN. The training process involved data loading, pre-processing, grayscale conversion, Gaussian blur, normalization, 8:2 train/test split, pixel feature standardization, and model training/evaluation, accuracy. Classification reports, confusion matrices. All models achieved over 60% accuracy, with random forest performing best at 74%. CNN training logs indicated mild overfitting. We performed precise measurement on radar-collected physiological data to acquire heart rate and respiration frequencies. The system loads raw radar data, performs range FFT on each frame, extracting complex phase information. Unwrapping and differentiation remove drift, highlighting movement-induced phase differences. Bandpass filters then isolate respiratory, 0.14 to 0.5 Hz, and heart rate, 0.7 to 2.5 Hz, signals. A sliding window algorithm removes abnormal fluctuations. Finally, Fourier transform converts filtered signals to BPM. Millimeter-level respiratory peak displacement is also calculated. Compared to smartwatches, Huawei, Apple, heart rate data showed high consistency, Pearson correlation coefficients of 0.93 and 0.94, with respiratory frequency error under 10%. Now, we will explain how Aurora assesses and alerts about risks. We have developed a unique risk index system, which consists of 3 key monitoring modules: lip recognition 50%, action recognition 30%, and breathing recognition 20%. The lip reading recognition system is the primary risk indicator. Once Aurora detects that the user utters words like dangerous that indicate danger, the system will immediately become highly alert and rapidly raise the risk index to the highest alert level. This is because language expression typically most directly reflects dangerous situations. The action recognition module is responsible for detecting abnormal physical movements. For instance, aggressive actions such as slapping, throwing a punch, or kicking will be quickly captured by the system and incorporated into the risk assessment. Its function is to monitor potential physical conflicts in real time and provide immediate behavioral warnings. Breath recognition. As a physiological state monitor for the system, Aurora can non-contactingly sense the user's breathing pattern and identify abnormal physiological signals, such as breathing disorders and rapid breathing rhythms. Although its weight is relatively low, in cases where the user is unable to speak or has restricted movement, it can accurately capture tension emotions and provide important auxiliary judgment for the system. Aurora will, based on the comprehensive analysis of these 3 modules, clearly categorize the risk levels into 3 states: green, low risk; yellow, medium risk; red, high risk. The system has detected a serious danger signal and will immediately activate the highest level alert, informing the user that they need to take immediate action or seek help. Aurora, an intelligent guardian, uses multi-dimensional information capture and intelligent analysis to assist users in identifying, warning of, and protecting against potential threats at an earlier stage. First, there is the visual feedback system. Our interface uses an intuitive color coding method. Green indicates a safe environment and users can feel at ease. Yellow indicates that caution is needed, as there are potential risks. Orange means that the danger level has escalated and immediate protective measures should be taken. Red indicates a high level of danger, and one must leave the scene immediately or seek help. This progressive color change enables users to clearly understand the current safety status. The next feature is the sound alert function. The system will issue corresponding alert sounds based on different risk levels. For minor risks, a soft sound will be emitted. For moderate risks, the sound will become more pronounced. In high-risk situations, the system will issue a rapid alarm sound to ensure that users' attention is drawn even in noisy environments. Aurora is always by her side, operating silently. It is the invisible guardian around a woman, a zero-presence security system. When it detects sudden movements, such as aggressive behavior, it triggers a silent alarm, immediately notifying emergency contacts and alerting community security, giving those in danger precious time. Aurora can also read lips. Even if no one hears a whispered "help" or "go away," Aurora can capture it. It regards every cry for help as the highest priority, ensuring that no call for help is overlooked. It also monitors breathing and heart rate and has safety thresholds. When these indicators exceed the set range, the system will initiate further analysis in a silent and precise manner to safeguard the physical and mental health of women. Aurora is an intelligent safety device specifically designed for women, combining advanced FMCW radar technology with feminist principles to provide not only protection, but also peace of mind and serenity. Through our research, we have uncovered a field brimming with potential at the intersection of radar sensing and machine learning, where technology illuminates entirely new possibilities. Aurora not only addresses today's urgent needs, but is also quietly shaping a future in which technology and compassion go hand in hand. With innovation, Aurora safeguards every calm breath and every precious moment.